Yeah, we have Fernando to tell us about binary codes.
Hello, everyone. Thanks for the opportunity to talk here, and thanks for coming. So I would like to give an introduction to binary code bounds. And we are going to start from the very basics, and we are going to progress from there. And hopefully, you're going to have a glimpse of the state of the art in terms of binary code bounds. So what is a binary code? So what is a binary code? And it's one of the simplest things that you can imagine. It's something that everybody knows. It's going to be any subset of binary strings is a binary code. We take any collection here in F2 today, we have a binary code. And here we can think that we have this big space, F2 today. You have F2 today. And then we have the code words, the elements of C. So, right, so those are the elements of C are called code words. C. And if you look at this space, it's tempting to try to come up with some distance metric, right? You would like to compare two code words. And one thing that you can do, you can look at the Hamming metric. So suppose that you have two guys, X and Y, and you can somehow count the number of positions that they disagree, right? So you can define a notion of distance between the points, which is the Hamming distance. And for two guys, X and Y, it's going to be just counting the number of positions where they disagree. So you sum from 1 all the way to n, and then you count xi different than xj. Very good. So this is a notion of distance. And ideally, in codes, you would like to make the code words as far apart as possible, because that's going to be related to the resilience of the code to errors. Right. So one important parameter of the code is when you look over all pairs of distance between different code words, and then you can take the minimum, right? And this is going to give the minimum distance of the code. So, right, you look at all pairs and so on. And here in this picture, let's say that it's a little bit further, it's realized here. So this is the minimum distance of the code, and it's a very important parameter of the code. So here, let's go to C. Is going to be the minimum over pairs, X different than Y, and Y belonging to our code, of their distance here, XY. Okay. So that's the first very important parameter. And the questions about the distance, it's just the usual Hamming distance that we have for binary strings. That's the first very important parameter that we need. Any questions about? No? Okay. All right. So this is the first key important parameter. And one thing that you observe by looking at pictures is that you also like to make the size of the code C we want as large as possible. So I give you, because typically what we think is that, I don't know, we have Alice and Bob, you have Alice, and we have Bob, and they are communicating. So here there is a channel, right? This is a channel, and we're going to think about the adversary channel. And the idea is that Alice has some message here. Let's say, I don't know, name bits. And she would like to send this message in a robust way across this channel. And what she's going to do, she's going to encode this message, adding some redundancy. So she's going, let's say that this is a message M, and then she's going to encode it using mapping this to some code word. So this is going to be a code word in some code. So this is going to be some x. And this code, let's suppose that it's a code in F2 to the n. Right, so it's as if this thing is going to be transformed into this x, and there's going to be a blow up in size in the number of bits that we represent. Right, so we have n bits here. So if you think about the true number of information symbols that we have here, so it's about m divided by n. So the remaining bits, they are redundancy. So 1 minus m divided by n is just redundancy to try to make this communication robust. Okay? And I give you'd like this ratio here to be as close to 1 as possible. You want to introduce as least redundancy as possible to achieve a given distance. So that's a communicating setting here. And this channel is allowed to flip adversarially, change a fraction of bits, change a delta fraction of symbols. So that's the whole of the channel here. This is the adversarial model of Hamming. This is called the Hamming model. And it's simple to see in this case that if you look at our code and you take two code words realizing this minimum distance, right? Suppose that this is some z and z prime, so they realize the minimum distance of the code, and then we can look at balls of radius a half, right? Radius a half here, radius a half of the distance, so this is distance divided by 2. And in the adversarial model, if you allow corruptions of more than delta divided by 2, it's as if you can go from the z, so this is prime, we have some z tilde here, some corrupted version, and then we can go all the way to some z tilde prime here, right? And if you allow more corruption than half of the distance, you might leave the unique decoding ball and land in the other ball, and then you cannot uniquely recover. Okay, so for unique recoverability in this setting, you can tolerate only half of the minimum distance, right? So for unique decoding, the radius that moves half of the minimum distance. That's why we want you to make the distance as large as possible. That's the unique decoding radius. All right. So we have this setting. And you might imagine that if you want to make the rate as large as possible, or equivalent, make the size as large as possible, there might be a trade-off between the two parameters, right? So let me move here. It's easier to see in a picture, so we have a trade-off. Between size and distance. Size here, and the distance of the code. And it's easy to see in a picture here. So if you have the entire space, and somehow our code has a small size, then we might be able to spread the strings quite well, right? And the minimum distance might become quite large in this case, right? So here is the case that the size of the code is small, and then we can achieve a large distance is large here. And then if you, in the same space, if you try to put too many code words, here we have F2 to the n, and now we put a lot of code words here. And then it might suffer, right? Two of the code words might become too close to each other here. So here you try to increase the size of the code, and then we suffered from a smaller distance. So this became small, all right? So we have this nice trade-off. And in coding theory, typically you would like to work with the normalized size here. So let's give this definition. So instead of working directly with size, coding theorists, they like to work with the rate. And that's going to be the second important parameter for us. And the rate is a notion of normalized size. So normalized size. And what you're going to do in the case of the binary case, you're going to define the rate of a code to be just the log base 2 of the size of the code divided by n. So this is the notion of the rate of the code. And we would like to understand the best trade-off between rate and distance, between size and distance, as we said before. And surprisingly, the exact trade-off is not known. And this is an important question in combinatorial coding theory. So if we ask what's the best trade-off between rate and distance, what is the best trade-off? Between the rate of the code versus the distance of the code. This is not known exactly. Not known exactly, which is very surprising. But a few things we do know in this regime, and that's something that we would like to cover here. So there are two quantities of importance in coding theory. One is that for a binary code, what is the largest size of binary code of block length n and distance d? So this is just the maximum. So here we have the size of the code. It's a binary code of block length n, binary strings of length n, and minimum distance at least d. This is a very important parameter, first one. And the second one is asymptotic rate. So if you want to understand this problem asymptotically, so someone gives us some distance parameter fractional from 0 to 1. And then here we have the asymptotic rate of delta. Sometimes we have a 2 to indicate binary code. This is the lim sup of sequence of codes of this normalized Hamming distance. So here we take n going to infinity, the lim sup of the rate of an optional code. So here we take log base 2 of a2 and you have delta n, delta times n, ceiling, divided by n. And this is of particular importance to us because here, if you improve the size of the code by polynomial factors, the asymptotic rate does not see it because of this normalization, it goes to 0. So we are really, when you consider this quantity here, you are really interested in the asymptotic growth of the code. If you even has polynomial and so on, really need to change this quantity by exponential factor. All right? And one important picture in coding theory, and now that there is going to be what is known, what is so we have this very important plot in coding theory, and there are many bounds, but we are going to focus only the two most important ones. So here we are going to have the asymptotic rate, r delta, and then here we are going to have the distance, the normalized distance delta. And for binary codes, here we're going to have a half. Very good. Here we're going to have rate 1. And then there is the first curve is an existential result. It's for random codes. So there is a first code here, first curve here. So this is called the Gilbert partial of bound. And we're going to.
It's worthwhile saying that you cannot expect better than a half.
Yes, very good, very good.
Because of this picture, you do over the.
Yeah. So the largest distance that you can expect to get a code of exponential size is at most a half. At a half, and later it's going to have vanishing rate. So for this picture, we do not see. Okay, but if very good. It will be a vanishing size if you go beyond that. And okay, so we have this Gilbert partial of bound, and we are going to explain this in more detail. And this is from the 50s, and this is the bound for random codes. So if you take a random code, either linear or general, and they're going to explain more, random code, we achieve this existential result that tells us that things up below here, they are possible. You can have combinations of rate and distance below this random curve. Okay? And this is not a very hard result to prove, and they're going to prove. And in terms of upper bounds, what you have is more complicated. We have a curve here, and I'm going to explain a little bit more. So above here, it's impossible. Impossible. And this is a result of McAllis, Rudnick, Ramsey, and Welsh in the 7-7. So they are saying that if you go a little bit above here, it's impossible. And that's just the names. Now let's give some parameters to see how those two curves are parameterized. And it's important to say that this result actually contains two bounds. So it contains a bound when the distance is reasonably large, 2.7 something here, 73. And this is called the first LP bound of MRRW. First LP bound. And this is based on the Hamming scheme, and we have a second one here, but we are going to focus on the first one. Okay? And in terms of parameterization, so what is this curve? So this curve is going to be the asymptotic rate, R delta, GV. So the GV bound establishes that the asymptotic rate of delta is going to be 1 minus binary entropy of delta. Okay, so let me move here. And binary entropy is what you know. We're going to have a delta log base 2 of 1 over delta plus 1 minus delta log base 2 of 1 over 1 minus delta. Okay, so we have here it's 1 delta. It's the usual binary entropy, nothing different, and the GV bound is establishing this for us. That with this kind of trade-off, you can have codes. Codes exist with this kind of trade-off. And the first LP bound is telling us, so we will write this R of LP bound. So this is of delta is going to be again the binary entropy of half, right there, half minus the square root of delta, 1 minus delta. Okay, very good. So we have these two bounds, right? And it's curious that the two bounds, they depend somehow on the entropy. And the binary entropy is somehow quantifying the volumes of balls in discrete space. So this is telling that the upper bound depends on the volume of some ball. And it's also telling here that the lower bound depends on the volume of the whole space divided by the volume of some ball. So the two bounds are related to size of balls. And looking at those functions here, it's hard to see what's going on, right? I look at them, it's not very clear. But
who is bigger?
Yes, who is bigger, right? It looks a bit ugly. But if you go to large distances for binary code, if you go to this part of the curve here that you're considering distance about half minus some epsilon, so the large distance regime for binary codes, then it's a bit easier to see the discrepancy between these two bounds. And this bound in this regime, so RLP, let me potentially go to the other picture, to the other side. So for distances that are quite large, so here we have the large distance regime of half minus epsilon. Then the R GV bound of this distance is going to tell us that rate omega epsilon squared is possible. And the R, the LP bound of this large distance is going to tell us that at best that you could do is epsilon squared log 1 over epsilon. So there is this log apart in the rate. It seems like nothing, but we have to remember that the size of an optimal code in this regime here, I'm using a little bit of the notation, is about 2 to the asymptotic rate, right? Times n. So it's an exponential, it's the base of an exponential growth. So it means that somehow we do not understand the base of this exponential growth. And the gap becomes larger and larger as we go further, as we take just larger and larger. So it's a pretty big gap. So you only know the size of the code up to exponential factors in the block length of the code, right? So questions so far about this, and that's something that coding theorists would like to understand exactly. So giving a distance parameter, what is the best rate that you can achieve, right? Questions so far? No? All right, so this is a problem in coding theory, as you said, and we mentioned that we have this is one of the simplest questions that you can ask for binary codes. You have this collection of strings, you ask about given a minimum distance, how large you can make this code. Very good. And if you do not like coding theory and you prefer graph theory, there is a connection, right, between this problem and the independence number of a graph, right? So, I encourage you to try to think about a graph such that an independent set in this graph corresponds to a code of minimum distance d and vice versa. So can you come up with a graph, let's say G indexed by the block length and minimum distance, such that an independent set in this graph, is if and only if C is a code in F2 today of minimum distance D. What is such a graph? So the vertex set of this graph is clear. You want binary strings, right? So the vertex set is the F2 today, right? And given two such binary strings, X and Y, we cannot put the two in the independent set if they are too close to each other. So if you take two guys in the vertex set and we connect them in our graph, if and only if their distance is X and Y, Y is here. It's from 1 all the way to D minus 1. So they are too close to each other, right? So if you have this graph, you can think that's sort of an exclusion graph, right? If I somehow select one of the strings, I cannot select the other one, right? So I think of this as some form of exclusion graph. Questions about our exclusion graph? The verts are binary strings, and you connect two of them if they are too close to each other. They violate the minimum distance. And then an independent set here corresponds precisely to linear code. And the linear code is an independent set in this graph, right? And why this is useful? Because it gives us a different perspective on this problem, right? So essentially what we just said is that A, 2, and D can be equivalently computed as the independence number of this graph, right? And that's something that we have a lot of tools in convex optimization to try to understand. So we somehow mentioned that LP bound, this LP is linear programming. So you're really bringing techniques of convex optimization to understand the LP bound for this problem. All right. And it also gives a very easy way to prove the Gilbert-Verschaff bound, right? From this exclusion graph. What is the trivial bound on the independence number of a graph? Of a general graph, right? Alpha of a general graph, but specialized to this case, it's trivially the vertex set of this graph divided by the degree plus 1, right? We can always have an independent set of at least the size, and specialized to our case, right? Our vertex set is 2 to the n. And what is the degree of our graph, right? Recall that we are connecting two guys if they are at that distance from 1 all the way to D minus 1. So the degree in this graph, degree of our graph GMD is roughly the volume of a ball in discrete space. So volume of a ball centered at 0 and of distance D minus 1. This is roughly what we have. Of course, we exclude the 0 word. So whenever you differ by something of Hamming weight from no, you need to subtract the 0, right? To not have
Minus 1.
Yes. Yeah. Now you're exact, and you can even cancel this. This was very good. And what is the volume of a ball in the discrete space, right? This is quantified by the entropy, right? And I think that this is one reason why entropy is a very natural quantity, right? So here, this is approximately 2 to the binary entropy of d minus 1 over n times a. And let's call this our delta, right? So this minus 1 here doesn't bother as much asymptotically. And what we're going to have here is that this is roughly 2 to the binary entropy of delta. And then we get that this is at least 2 to the 1 minus the binary entropy of delta. All that delta for us here is roughly d divided by n. Right, this minus 1 we are ignoring. So we have this, and we prove that the Gilbert-Rashomon bound. Very simple, trivial, right? We do not know how to do better than this, right? So we are still stuck. This is a result from the 50s, right? And we do not know how to do better. You are missing
the denominator.
Oh yeah, thank you, very good. Yeah, thank you. And this also holds. So Gilbert proved this for general codes, and Rashomon proved this for linear codes. Let's go to linear codes. Just okay. So it's the Gilbert-Rashomon bound we call GV, and Gilbert proved the first result, and Rashomon proved the second one for linear codes. It also holds for linear codes. And just to try to establish some notation, because we are going to focus a little bit on linear codes. A linear code now is not any subset of f to the n, but it requires to be a subspace, right? Now it's a subspace. And two things are a little bit simpler now. If you want to compute the rate of this code, it's nothing more than the dimension of the code, because it has two the dimension string, so the dimension of c divided by n. Now the rate becomes a little bit simpler, and the distance, the minimum distance of the code, now it's also simpler, right? So it's going to be the minimum Hamming weight. So here, if you take a guy in our code that's not 0, different than 0 Hamming weight, then we look at Hamming norm. So we are just counting the number of positions that it's not 0, right? Let's recall that the extended thing. So x is just the number of positions that this guy is non-zero. So for linear code, it becomes this, right? Because you're comparing two distinct code words, right? In the minimum distance, in the definition of the minimum distance. But you could subtract them and look at their norm. But the subtraction is again a code word in your code because of linearity. So it suffices to look at the minimum Hamming weight of the code. So exercise. And what Rashomon said is that, and one way of encoding a linear code is if you take a matrix of, let's say that we want a code of the dimension of the code is k. And then we can think that it's given by a generator matrix here. F2 times k. So this is a generator matrix. So our code is going to be precisely the image of this matrix. And a trivial random model would be to select the entries here in the form at random, right? And if you take a G completely uniform here in f2 to the n, we are simplifying a bit because this might lead to a matrix that does not have linear independent columns, right? But it's a simple random model. And now one thing that we need to understand, if you take something that's, let me call this another name, Z belonging to Fk, right? And then you look at this quantity, suppose that this guy is different than zero, and then we look at this quantity here, the marginal distribution of this guy over a random choice of G is uniform, right? Again, in the space. So if you're interested in the probability over a choice of G uniform of the Hamming weight of this guy for a non-zero guy becoming smaller than, I don't know, d minus 1, this is going to again appear the volume of the ball. This guy is uniform, and then this is roughly the volume of the ball. The same computation is going to apply. Let me press and simplify. Divide by 2 today. And then you can run a union bound argument, right? And then get a k that's exactly the k that we had before. All right, so it also holds for linear codes. Very simple, and that's the best that we know. You're showing this, it's simple, but this is the state of the art in terms of explicit construction in this curve. So in this curve, we have this delta that's free, and the best that we can do asymptotically is this. We know how there are some codes that beat the GV bound, but by polynomial factors. And then the asymptotic rate does not see it, right? Because the
do we know if the GV bound is tight for random codes?
If the GV bound is, I think it's derived from random codes, I would expect the answer is yes.
We don't know that?
I would expect that the answer is yes, that the analysis is tight. But yeah, I would think that yes, Rui, but
it should be from concentration.
I think so. I think so.
It shouldn't be.
Yeah, I'll be surprised if it's not, but let not put my hand on fire.
Thank you.
But to have something very simple to me is.
Did you consider the question of whether it's possible that the optimal code must be linear?
Yes, that's a very good question, and I think this is related to even to the packing in Rn. So people consider lattice packings that will be analogous to linear codes and non-lattice packings. At least in Rn, people believe that lattice packings they might not be the best. I don't know for linear codes; it's a very different binary codes, a very different setting. So I don't know what is the belief of people, but the bounds that we know for linear and non-linear at this point they are the same, the lower and the upper bounds. All right. Okay, so asymptotically, yes. And it's important to stress that if you want constant distance, not relative distance, then you might have perfect codes. And if you go to stupidly large distance, that this delta, and this epsilon is a vanishing function of n, then different things are known. So here we're thinking that we have a delta that we can choose, and then you're letting n go to infinity. So it's a regime of good codes, right? So it's a all right. So so now we are done with the Gilbert version of proof, and now let's move to the upper bounds, right? And the upper bounds, they are going to rely on this equivalence, right? This quantity here is, well, at least some of them, but let's go slowly. Okay. Very good. So now let's go to the side of impossibility results. Possibility. And one very nice thing that appeared in this literature is something that's called Williams Identities. And we are going to explain this. So suppose that we have C, it's a linear code, F2 to the n, and then we can somehow count the number of code words of Hamming weight 0, 1, 2, all the way to n, right? So you can define what it was. So AI is just going to be the number of x in our code, such that the Hamming weight of this guy is precisely I. Very good. And with this, we can form a vector, right? A0, A1, etc., all the way to AN. This is going to be a tuple here, right? Plus 1 entries. And this is called the weight distribution of the code. Weight distribution. Code. And one nice thing, you can look at the dual of this code. So you have a linear code, and you can look at the dual. The dual of a linear code is going to be all the guys in the space, such that when you look at this by linear form, it's 0 for every guy in the code. Every we're going to see. So that's the notion of the dual code.
So it's the kernel of this matrix G.
Is the kernel of this matrix G. It would be, let me think, if you had the pair check matrix of the code, it would be the row space of the pair check matrix, which is also.
So in the case of, so the image of the code GC was the image of G. And
so it's definitely the row space of the pair check matrix.
Kernel would have the right.
No, if the dimension is 4. The dimension is 4.
No, the kernel lives in a space of dimension.
So the row space.
Okay.
The row space is the dual, and this is the pair check.
Okay,
So
right.
here you have an equivalent definition of a code. That's the kernel of the pair check. Yeah.
I think it's like the parity check matrix of the dual code or something like that.
Yeah.
But we can look now at the weight distribution of the dual, right? We have B0, B1, all the way to some Bn. It's the weight distribution of the dual. This was of C. And let's say that now we have of C perp. And you may ask, is there any relation of the weight distribution of the primal and the dual? Is there some transformation that can take one to the other? And this was, I think, a very cute thing that McAllister observed, McWilliams. So McWilliams, it's a cute little result that tells us that you cannot obtain the weight distribution of the dual from the weight distribution of the prime. And the way to do that is that, so beta I of the dual is going to be 1 over the size of the code, summation here of j equals to 0 all the way to n. And then here we have some coefficients. Let's explain what those coefficients are. Times aj. So those are going to be scalars in the real. So there's sort of a linear transformation up to the size of the code that take us the weight configuration. If you know the weight distribution of the primary, you can get the weight distribution of the dual. So this is for OI belong to 0 all the way to n. And those are called McWilliams identities. And those guys here, they play an important role in the theory. They are called the Crotch of Polynomials, and we are going to define them. Okay? So K, I, X. This is the degree. Degree I, Crotch of Polynomial. And there are many ways of writing this Crotch. Coding theory, I think this might be the most standard one. Crotch of Polynomial. So, and it forms a family of orthogonal polynomials under the binomial measure here. So here, this is going to be this space we endow with the and with this binomial distribution. I is chosen with probability and choose I divided by 2 today. And they form an orthogonal family of polynomials, and they are going to define them. Right? And what is the definition of the Crotch of polynomial? It's a very simple thing. So, suppose here that we have our space, our discrete space, F2 to the n, and we can look at a sphere of radius I. So suppose that this is some sphere of radius I. And let's take the indicator of code words of words of Hemingway I. So we can look at a sphere in discrete space, right? And this indicator of some y is going to be 1 if the Hemingway of this guy is beside the I, and 0 otherwise. What is the Crotch of polynomial here? So Ki of j, here we are going to need to take some character of Hemingway, going to define those things, Hemingway j, and we look at 2 to the n, indicator of this Hemingway, indicator of the sphere, and here we do the Fourier transform of that. So you're essentially, so here you can take, I'm using this identification that a subset of F2 to the n can be encoded as some string, right? You can also think of this as a guy, I'm using the notation as a guy in F2 to the n, the indicator of this, right? So if you want to evaluate the Crotch I at j, you take any subset of size precise j, and then you look at the Fourier transform of the indicator and you evaluate it as. So this is the Crotch of polynomial. So it's, in a sense, it's a Fourier transform of this sphere. Okay, very good. And it's indeed.
It will be the same for every set.
It's going to be the same, yes. Yes. You can symmetrize. This set is certainly symmetric, right, with respect to the action of Sn. So it doesn't matter the choice. The only thing that matters here is the size, is the Hemingway of this. So you're doing the Fourier transform of the sphere. So it's a very natural thing. And to define the, okay, so with this you can understand, at least again, the statement of the Williams, and let's prove. It's very simple to prove. And let's show proof of this. You can even guess what the proof is going to be. So we are interested in counting this quantity here, beta I, the number of code words of the dual that have a given Hemingway, right? And how you can do this? We can take an inner product, right? My inner product is going to be normalized. That's why we have this. And what should I put here? It's an inner product that's normalized. And the idea is inner product of two functions. Let me help with the first one. It's going to be the indicator of the dual. And what should we put for the first one? We are trying to count the number of code words of the dual that have Hemingway I. Here, my inner product is normalized. That's why I'm multiplying by 2 to the n. And here I need another indicator. Very good, very good. Indicator of the sphere I, right? Indicator of double I. And you are working, you want to do Fourier analysis here. So you have an inner product, let's compute this in the Fourier base, right? And if you compute this thing in the Fourier base, what you're going to have is, by Plancherel, you're going to have all sets in N. So here, let me put together this guy, 2 to the n in this guy, and double I, Fourier transform of S, and then the Fourier transform of C perp at this. And let's explore this guy. What is the Fourier transform of a linear code? And it admits a very nice expression. When probably already tell me the answer somehow. So the little plane is that if you have a linear code, see linear, then if you look at the Fourier transform of its indicator at S, it's going to have a very nice expression. And what should be this expression, right? This, by definition here, the Fourier transform of S is going to be the expectation y dash then. And here we have the indicator of the code at y. Then we have chi-s of y. And if S, so we are only considering, because of this indicator, we only consider y's in the code, right? And whenever S is in the dual, this is going to evaluate 1. Because recall that the inner product of S and Y, for if S belongs to the dual, it is always 0, right? And then this always evaluates 1. And then this is just a fraction, right? So this is going to be the size of the code divided by 2 to the n, if S belongs to the dual. And in the other case, what's going to happen? It means that there is a guy. So we have our code, and there's going to be some x in our code that I don't know, S x evaluates 1, right? So we have this x here. So this is our code, and here we have a part that evaluates to 0. So everything here, this point is going to be 1. And everything in this part is going to evaluate, this character is going to evaluate to -1. And by summing x, whatever is here, if you take the max, the mapping that adds x, you go from one to the other, and then you have a bijection. So the number of -1s and 1s is balanced, and then you get a 0. If it's not in the dual, right? Because with 0, this evaluates 1, and with x is evaluates -1, and you have this nice bijection between the two. And then we can say that this is the size of the code divided by 2 to the n, the indicator of the dual, right? This completes our little claim, and now we can apply this here, right? And this is going to become C-perp divided by 2 to the n, indicator of the prime. Yes, right? Very good. And now we can combine things by Hamming weight, right? We can instead, let's move this term in front. This is 1 over C, right? This is 1 over C. Then you have the summation. Now let's group things by Hamming weight. J equals to 0 all the way to n. This became our Crotch, as we said. This is Crotch I evaluated at Hamming weight of S. And if you look at all the guys that have a given Hamming weight J, and you sum over them, you're going to get the Crotch ij times aj. And that gives us the Williams identities that we promised before. Good. So there is a nice cute relation between the weight distribution of a code and its dual, right? And with this in mind, we can try to come up with a linear problem, right? You're trying to understand A2 and D, right? And how would you come up with a linear relaxation, something that might be give an upper bound for the size of the code? How any ideas for how to come up with an LP? Well, it's the most natural thing that you might imagine. The objective function is going to be the max of the summation overall possible Hamming weights from 1 all the way to n of aj. So this is going to find the size, trying to capture the size of the code. Right? If you have a linear code, there's some of the code. All right. And now we have some constraints, right? If you have a linear code, how many guys of Hamming weight 0 we have? Exactly 1, right? It's a linear code that has a 0 vector. And we need to satisfy minimum distance constraints, right? A1 all the way to A2, all the way to AD minus 1. This is equal to 0. Because this is related to the minimum distance constraint. Minimum distance constraint. And this is going to be a relaxation. I should have mentioned this, a relaxation for the largest size of a binary code of block length n and minimum distance t, right? Right, so we have the normalization, we have these minimum distance constraints. What else can we include here? We have seen that if the AIs, it's a relaxation. So we are going to have the AJs being greater or equal than 0 because they are counting something, right? But they may not correspond to actual weight distribution, right? It's an LP relaxation. But we can certainly consider the Crotch transform, right? So in this transform here, in particular, since this is counting something, we will get inequalities for free, right? Greater or equal than 0. And then we can remove this normalization and work with this set of asking this transformation to yield some value that's greater or equal than 0. If you had a true code, it would give us that, right? And then here we have the summation of k, I, j, aj, j equals to 0 all the way to n, greater or equal than 0. All right, so for all j, impose this. What? Oh, I, very good. Very good. We're awake. And this is known as Delsarte's linear program. So this is the famous Delsarte's LP. And we mentioned, we stated the problem for linear codes, but it works more generally for nonlinear codes. We are going to get there. This is Delsarte's. It's one of Delsarte's linear programs. And this is around 73. Around 73, this is around 663. And if you generalize, and I'm not going to prove this, but if you have a general code, you can generalize the notion of weight distribution to distance distribution. And that program, the McWilliams inequalities are going to hold in that setting, and also the Delsarte LP. Let me just state the definition of the distance distribution. And the proof generalized easily. It's not very hard, but I think the linear case is a bit cleaner to see things. And if you have C containing a 2 to the n arbitrary, now not necessarily linear, we have this notion here of AI being equal to 1 over the size of the code. Here we are going to look at pairs, x, y in the code that are at a distance I, x, y. And then the same theory would apply here for general codes.
The size of it.
Size? Oh, the size, yes, very good. All right. And the first LP bound is going to be an analysis of this guy here. So we have this family of linear programs, and somehow you need to give a theoretical analysis of this family, right? And one way of giving bounds for this, you go to the dual, and then you try to cook a dual feasible solution that might have a good, might give a good upper bound on this guy here. And that was the result of McAllis et al., right? But before you go that, let's talk about another way of here we have a relaxation for the H2N, right? Now let's come from a different perspective. Let's look at this problem as an independent set on a graph. And with this, you're going to have a variation of the Lagrange theta function of a graph. That's called the theta prime. So now let's consider a function that is going to be a relaxation. Let's use a graph already. That's a relaxation for alpha for the independence number of this graph. It's a strengthening of this is from Shriver. Around 79. And this is stronger, a little bit stronger, not that much, than the louvers, the usual louvers. lowest theta function. What is this relaxation now? So here it's going to be a semi-definite program. It's going to be an SDP, and the objection function here is we are going to maximize the trace of J times N. So this is the all-ones matrix. Then we are going to add some constraints, such that this is going to be a matrix that lives in the vertex set, not the vertex set. We want this matrix to be PSD. We are doing a semi-definite program, right? We want all the entries in V to be greater or equal than 0. And that's why this is the condition that's the strengthening of the theta function for all vertices U and V. Into a graph. And we also want to enforce that whenever we have an edge, the corresponding entry is 0, because we are trying to do independent set for every UV belonging to the edge set of our graph G and D. So this is a relaxation for the independence number of the graph. And notice that this program is huge, right? The matrix that
maybe before you want to show why an independent set gives a lower bound of this.
Yes, yes.
Any independent set satisfies.
Yes. How can I go? Suppose that I have a S containing V, that's an independent set. How is this a feasible? How can we come up with a feasible solution having this independent set in our hands? Oh, I forgot normalization condition. So the trace of this matrix is 1. Explodes. So how can we come up with a matrix M? That's a feasible solution to this. We can take M to be the indicator of the set, right? The indicator of the set transpose divided by the size of the set. This is certainly PSD.
It's a tensor product, right? It's an all-ones matrix.
Yeah.
Yeah.
It's an exterior product.
Yeah.
Yes. The exterior product. Mm-hmm. Yeah. It's definitely PSD. It has the correct dimensions. It's definitely 0 because you are dealing with an independent set. The normalization is 1, and the objection value is precisely S. Right. So it's definitely a relaxation for the independent set. So now we have this very powerful SDP, right? Very powerful SDP. This matrix has 2 to the n. It's a matrix of 2 to the n by 2 to the n. And on the other side, we have Delsarte's LP, which is a matrix of n plus 1 variables, it's a linear program, right? Which one do you think is going to give a better bound, or is it stronger? Or it's a tricky question. They are actually the same thing in disguise. So the graphs that we are working on, they have a lot of symmetries, right? This graph here has a lot of symmetries, and its symmetry group is a semi-direct F2 to the n. And if somehow you take this program and you symmetrize, you get Delsarte's linear program. So in a certain sense, this, and you might be asking, where is the PSD conditioning, this constraint coming from? So the Mac-Williams inequalities here, they are actually checking PSDs. They are sort of equivalent to checking PSDs. But now it's a much smaller program. So we have these 2 ways of looking at the Delsarte LP, and this correspondence was established by Schreiber. Schreiber observed that if you strengthen a little bit the theta function of Lopez, you will get this equivalence.
Okay.
What?
Even more generally, Schreiber observed association.
Yes. Even for more general association schemes. Very good. So let's just move faster. I think it's slow. Let me show a proof of the first Machiavelli's proof, first LP bound. See if I want to save this. Let's give a modern proof of the Machiavelli's et al. Bound. So the original proof, what they did, they went for the dual of this beast, the dual of Delsarte, and they took a feasible solution. And that's very tricky because those Crotch of Polynomials here, they are complicated. They have a lot of alternation and so on. It's really impressive that Machiavelli's et al. Managed to analyze the dual of this. But now we know more modern ways of presenting this. this proof using only Fourier analysis and a bit of spectral graph theory. Let's try to go for that. And it's a proof of Navalness homogeneistic. Around 2005, and it's building from a work of Fernando and Tillich, which really managed to simplify the picture here. The mechanism is complicated, and it's going to be a bit of Fourier analysis, basic Fourier analysis, and spectral graph theory. And the idea is that what we're doing is a packing problem, right? So we have this space F2 today, and we're trying to pack with balls of radius, the distance divided by 2, roughly, and put as many as possible. It's a packing problem. And sometimes a covering problem might be easier if you go to the dual and try to cover the space. So one thing that they're going to try to shoot for is that we have our space F2 today here. And now, instead of considering the original problem, packing problem, let's consider, we should do this, let me make it smaller. So here we have F2 today, and you'd like to consider a covering problem. Covering problem. But from the perspective of the dual, right? So we have this three-dimensional inequality. So the size of the code is 2 to the n divided by the size of the dual. And if you want to give an upper bound on the size of the code, it suffices to prove that the dual is large, right? To show that C is small, very vaguely speaking, then it suffices to show that the dual is large. Large and small means. And here you're, instead of working with the primal code, let's work with the dual code. But let's consider the code words of the dual. So those are going to be code words of the dual. And we have our space here, and with a bunch of code words here and so on. And so somehow let's suppose that you're going to have some radius R. So let's say that we take a radius R of n. And let's think that this radius is quite small. And what we're going to try to do, we are going to try to cover the whole space using centers as the dual code words, using balls of small radius, right? Suppose that somehow using very small balls, we manage to approximately cover this very large space F2 today, right? So those are balls of radius R.
Yeah, you should have overlap. So
yes.
It's clear that you want to cover everyone.
Yeah, we have a lot of overlaps, and we have a lot of those small balls. That's why I was trying to draw it as a smaller picture. But we really have a covering of this space. An essential cover of the space. Cover this space up to polynomial factors, but polynomial factors do not matter for us. Polynomial n, and so on. So it's really a covering problem. So if somehow we manage to show that the entire huge space F2 to the n is roughly covered by balls unit with centers in the dual of very small radius, right? B, X, R. What that's going to tell us? That's going to tell us that 2 to the n is at most the size of the dual, because that's the number of centers, and the binary entropy again. H R divided by n times n. And then if you pass this to the other side, we get precisely the size of the code divided by 2 to the binary entropy of R divided by n times n. So we will get a bound here. Right? So if somehow we manage to approximately cover the entire space using small balls centered at dual code words, we prove an upper bound on the side of the code. Right? And not surprisingly, the size of this radius is going to amount to being that radius that we have in the Michaelis et al. That's something that's going to be possible to take. All right, so let's go to the proof of this this thing. The proof is not very complicated, and we are going to need the spectral lemma. We are going to need the spectral lemma. Question so far? Is everything clear? Then the strategy that we're doing. Okay, so we have this lemma, which is a spectral lemma. Call it spectral lemma. Okay. Very good. And what it tells us that given any choice of radius that you want, from 1 up to n, there's going to be a function that's going to depend, of course, on this choice of radius. It's a function on the vertex of the Boolean cube to the non-negative real. So here we have r greater or equal than 0. And it has a few properties, such that the first property is that the support of this function, the non-zero entries, they are all contained in the ball. So here f, support of f is contained in the ball of 0 of radius r. Very good. And another thing, and let me potentially, is that pointwise when I apply f, so this is the adjacency matrix of the Boolean cube. So not normalized adjacency matrix of the usual named Boolean cube. In cube. So this is the usual adjacency matrix of the Boolean cube. And then when I apply to f, you get something that's pointwise greater or equal than a lambda times f. That's pointwise bound. And where this lambda is at least 2 to the radius that you decided to have, n minus r, and then minus some little of a term, minus some error here. So what went on here? So with this lemma, for any choice of radius that we want, we can get a function on the vertex of the cube that's non-negative, and such that the support of this function is contained in the ball. And if I apply the Boolean cube to this function, pointwise, we get lambda f, where lambda is this thing that depends on, of course, on the radius that we chose. Okay, very good. And it's a technical lemma. Let's not prove it now. Let's continue with the proof. I can potentially say a few words if you're interested in how to prove. It's a computation, not too hard. All right. And now let's try to implement our strategy, our covering strategy that we mentioned before. And one way of implementing this strategy is an analytic way of implementing this strategy. So an analytic way of implementing this strategy. Way of implementing the strategy, what would be? So there is a radius r that is going to be chosen later. Radius should be decided later. Decided later, whatever this abbreviation means. Here we use the spectral lemma. Spectral lemma there, and then we get a function f related to this radius. And what we're going to do, we are going to cook a new function, a capital F function, that's going to be the convolution of this little f with the indicator of the dual. So it's as if you look at the support of this, you're going to this function support non-balls, right? Of radius r. And this is centered at the dual code words. And then you're having the convolution of these two functions. That's going to be an analytic way of implementing that strategy. So in particular, you're interested in the support of this function. So what is the support or size of this function? What is the support size of That's something that you're going to need. And to understand that,
You want it to be everything.
we want to be very close to everything. It's okay to err by polynomial factors. If you're off by polynomial factors, the symptotic rate does not see it. So you're going to be almost everything. And one way of trying to understand support is to somehow derive some inequalities of the second moment of the function squared with some inequality with some small constant here, and the first moment whole squared. So you're going to try to derive some sort of analytic version of this. With this, you can do some support lower bounds. But let's keep this aside and then let's continue our investigation. And one thing that we're going to analyze now, in order to deduce this, is going to be a quadratic form. So we have the adjacency matrix of the cube again, the n cube, have this matrix F, and we are going to look at this quadratic form and give lowers and upper bounds to this quadratic form, right? Very good. Before we do so, let's just say a few things about what happens when we multiply by A. The claim that is the little claim, and that's very simple. The claim is that if you take a function and you multiply this by the cube, so this is the adjacency matrix of the cube, this is going to be the same effect as convolving, right? With some L, where L is going to be 2 to the n, the indicator of Hemingway 1. 2 to the L, okay?
It's a neighborhood. You have a number of neighbors.
Perfect. All right, having this, now you have another claim. It's also going to be immediate. Here, if you look at the Fourier transform of this function here, what that's going to be from what we have seen before. So we can use the convolution. The convolution is going to become a product, right? So you're going to have this pointwise with G, right? And what is this guy? Something that we have already seen. This is Crotch of 1, right? This is Crotch of 1. Evaluated that size of S, because it's a symmetric function, times G hat. And for the Wien cube, you know precisely the eigenvalues, right? This Crotch of 1 is 2 times n minus 2 times the size of S. Right? Those are the eigenvalues of the Wien cube. This is also Crotch of 1. All right, question about these two claims here. So we are just applying, we are using this and applying the Fourier transform. And for the convolution, it becomes a pointwise product. Nothing serious happened here. And now let's give bounds, right? We have this quantity. Let's start by trying to understand what's going on here. So we have this, and we sort of said that the action of A is the convolution, right? So we can equivalently write this as L convolved with F, but F is F convolved with the indicator of the dual, right? This is our F. And we can use associativity to evaluate this first, right? Put the parentheses here and evaluate this part first. This is the same as A times F, but F is a function from our spectral lambda, right? We know that pointwise it's greater or equal than 1 to F. Right, so that's coming there. This is a non-negative function, right? So we know that overall this thing is at least lambda f, because this guy is at least lambda f, and then convolved with the indicator of the dual. And this becomes f again, right? So this becomes lambda f. And if you plug here, this means that this is at least lambda F with F. That gives us a lower bound. Very good. Now let's try to give an upper bound on this beast, and the distance of the code is going to appear for us. And how can we give an upper bound? So we are evaluating an inner product, and we want to do Fourier analysis. What we do, we do Plancherel, right? So we have the summation of S contained in N of AF hat. S, and then here F hat of S. But we have seen we can use this lemma here to bring the Crotch to the picture. And this is going to be the summation of S containing n, n minus 2s, that's the Crotch of 1. And then here we have f hat S whole squared. Very good. And you want to understand the Fourier transform of this function here, right? And if apply the Fourier transform here, what we're going to get is a pointwise product again, right? So f hat is going to be Fourier transform of this, pointwise, the Fourier transform of the indicator of the dual. But we have seen that this is proportional to the indicator of the primal code. And the primal code has minimum distance, right? At least this is C perp divided by 2 to the n, and then f hat, the indicator of the code itself, right? So we will go back to the indicator of the code. This expression, the indicator of the code has minimum distance, at least d. So whenever you see something whenever you plug some set that has size between 1 and d minus 1, this guy is 0. The Fourier transform vanishes there, right? So let's single out first the 0, the empty set. So we have, for the empty set, we have n times f hat of the empty set squared plus, and whenever this quantity is between 1 and d minus 1, we know that this guy vanishes, is 0, right? So we have that this becomes a summation of guys containing n, where the size of the set is at least d. And then here we have n minus 2s of f hat s is squared, right? Very good. And we know that we are only considering guys of Hamming weight d or larger, right? So in particular, what we can do, we can make an inequality here and say that we are going to plug d here, right? Instead of s, we will plug a d. So we have an inequality. And now instead of just summing over guys that are greater than d, let's overshoot, let's sum over the entire thing again, right? An inequality again. And then we have this. Very good. And what is this part here? So this part is just the expected value of the function whole squared. This part here becomes the expected value of the function whole squared. And here, when you sum over everything again, you get the inner product of the function with itself, right? By puncture. So we have n minus 2d. Then here we are going to have f. Right, so this becomes an upper bound on this quantity here, right? This becomes that upper bound. And let's combine the two to see if you can derive something to give an inequality of that form. And very good. And that somehow is going to inform us the parameter trade-offs that we're going to have. So if you move this part here to the other side, what we're going to have is lambda minus n minus 2d. And then here, the inner product of f with itself, smaller or equal than n times expectation of f whole squared. Right? And we are going to choose an R such that this quantity here is going to be at least 1. So we are going to choose R to have this property. And they're going to see how the parameters they are going to fare with each other. But and what is this? This is simply the second moment of the function, right? The expectation of the function squared. So if assuming that we have a good choice of R, we get this inequality here. An n with an n here. And with this, we can derive some support lower bounds, right? Let's raise the bar. here, what we have the expectation of f, let's say that the whole square. And one thing that we can do that will not change this is to use the indicator of the support, right? Of course, you can say that this is capital F, the indicator of its support. This is not changing this expression, right? And then we will do some Cauchy forms, right? Here you're going to have f squared, and then here you're going to have the expectation of the indicator of the support of f. Very good. And now we know an upper bound for this, right? That we are assuming that we have that's this thing squared is n times e squared, right? So this is n times the first moment whole squared, and then this is just the support size of f divided by 2 to the n. Then it cancels, right? So here we have this, cancels with this, and then we move the 2 to the n. We deduce that the support size of f, support size, is large, it's quite large. It's at least 2 to the n divided by n. And that's very good for our strategy. We are essentially covering. If you put a function that supports non-balls, convolved with the indicator of the dual code, you are essentially the support of this function essentially covers the entire space up to polynomial factors. Right? And this is implementing the analytic strategy that we mentioned. But we need to work out the trade-off here, right? Why you can get this trade-off that we mentioned. Let's just do a quick sketch of why we are going to get that radius there. And let's massage this a little bit. So you have n 1 minus 2 delta. And delta for us is the normalized distance, is the over n. Right? Very good. And the radius that we have, that lambda is at least, from that assumption there, is 2 times n. Let me already simplify there, tau 1 minus tau. Where tau, I'm going also to normalize the radius. Tau is going to be the radius divided by n. Right, so here we have 2 times the square root of the radius times the thing. So one thing that you could do is divide the 2 by n and put an n in evidence, and then call this guy here tau. R divided by n becomes tau for us. Okay, and then we have this trade-off, and the claim is that okay, we have this. Let's choose what is the choice of tau that. Not surprisingly, you're going to take. You're going to take tau to be the Michaelis, and then see that this roughly holds the computation. We need to be a little bit more careful, right? But just to give a flavor that this might be ballpark. So 1 minus delta. And if you plug this here, what you get is 2 times n. And here we have the square root of f minus square root of delta, 1 minus delta, 1 times f plus square root of delta, 1 minus delta. And we can cancel, we can remove these 2 2's inside the square root to cancel this guy, right? So we get this, that this is n, the square root of 1 minus 4 delta squared. I'm already jumping a few steps. Delta squared, we get this quench inside, and this is n divided by 1 minus 2 delta squared. And then this becomes 1 minus 2 delta. Okay, and it matches perfectly. So instead of a 1, we got a 0. So if you want to get a 1, you need to do it more precisely. Okay? But it illustrates that if you choose this radius here, we are in a great shape, right? And we know that essentially the size of the code becomes the size of those balls that we use in the dual, right? From what we said initially, right? So with this, what we conclude? Let's just. So what is the support? So one index. So we have 2 to the n divided by n we have the support of F. And the support of F is bounded by the number of dual code words and the volume of the ball. The same computation that we did in the beginning of radius R divided by N times N. And then with the same computation, a little bit more precise, because now we have N, get that the size of the code is at most 2 to the, and this is our tau that we chose before. This is at most F minus square root of delta, 1 minus delta, binary times N. And that's exactly the first MRR. RW, first self bound.
Upper bound is
Okay.
so if this upper bound is tight, then it means that the covering radius and the distance are basically the same.
You're saying,
Yeah, if you look at two problems, in the space of 2 to the n, what is the largest size of a code you can have with distance d, and what is the minimum size of a code you can have with the covering, which covers the radius.
if this method is optional.
If this is optimal, then these numbers are essentially the same.
Yes.
And otherwise, this R is a factor log 1 over, at least in the near half range, it's a factor log 1 over epsilon apart in the exponent. So I mean, is it known for other spaces that covering radius and distance are the same?
I don't know what. Don't know.
Is it known when it's different? I mean, are there examples of any spaces, any metric spaces where you know that they shouldn't be the same?
Not that I know. And more focus on the binary case, and even in those discrete spaces, as you change the alphabet, the picture changes very dramatically, right? And the little that I understand about Rn, those packing, coverings, and etc., it seems that a lot is unknown there as well. So it seems that asymptotically we know that there's a lot to be known just to know those problems. But I don't know. But at this point, it's completely open. We do not know if this bound is the correct one or the GV bound is the correct one. One interesting thing that
we get the same problem, because on the covering side there is no distance.
The radius is
Right, there's the radius, but
that's what is called the covering radius. It's the dual problem to solve if you
sure,
want
but you're only getting, when you do this proof, you're only getting duals that come from codes that have some distance, right?
No, I know, but I'm not thinking, these are duals for codes that come from distance.
Yeah, so unless you put this into the covering problem.
Yeah, that's a good thing. Yeah, if you look for a covering, it's covering by any.
Yeah, by any code, it could be better.
That's a good point. Yes.
At least a priori. I mean, don't know if fact.
Yeah, you think that these points be far apart to cover the thing well.
No, but they should be far apart on the dual, but you don't know about.
No, I know, but we restricted C curve so that we restricted C curve so that C has
So if you're taking the covering problem, you're getting some weird restriction that you're saying, I want to cover my balls over some folds, and dual of this code needs to have some distance.
That's very weird. Yeah, it's all
So one message here is that we have those. This proof of Navalness homogeneity can also be seen as giving a dual feasible solution to this. Okay.
I'd like to ask about the previous.
Oh yes, please.
Perhaps I can ask for some intuition that's less algebraic and more, algorithmic for the definition of this big F of the covering.
Oh, the only thing that I see is this analytic one, that you have the space, you have centers that are at the dual, and somehow you want to place balls around those centers in order to try to cover the space. And sometimes trying to understand this covering is equivalent to understanding the support size of this function.
Yeah,
That's sort of the.
Here, I got it, but you don't place it at the center, right? And you don't place the covering at the specific centers, you place it around them, right? This is the definition of this big F.
Yeah, you're going to do the convolution here. So it's not, you're not potentially exactly doing this, right? It's a bit more messy what's going on.
But maybe you should say that, yeah, if F was itself the indicator function of a ball.
Yes, that's a.
But it was an indicator function of a
If the small F, you mean?
Yeah, smaller.
Smaller. If it was, you could have taken it to be that. Then it would be exactly, you will just get, the convolution will be exactly the size of the ball. Good. So, but you don't know what to do with this. So you are looking for functions that looks like it, right? That maybe it's not a 0-1 function.
Okay, so it's a smoothing of.
It's a smoothing, absolutely. It's a smoothing. And so the demand there that it will have, the Fourier transform will have support in this radio, in this ball. It's sort of capturing, the way it simulates, right? The way it simulates indicator function.
Okay, I get the intuition that you gave me. I must say that I don't have it in my head how this covering will actually look like.
One potentially worse thing that I can say is that the Mac-Alice tall proof is extremely opaque. If you see, this is hard. It's a blessing that we have this. And I think one thing that this problem is quite hard is that it's very hard to see the structure with bare eyes, right? You're typically using tools to try to, I don't know, capture this problem.
You also don't hope to know what this covering looks like, because this covering is centered on the dual code of a code that's given to you adversarial.
Yeah, okay, but I can imagine like an algorithm that gets an adversarial dual code and does something to it to get a covering. This is an algorithm that I can think.
Yeah, but this function is determined. This function is something you compute. It's some sort of curve.
Some sort of curve.
Yeah, there's a function that is saying, well, if it's 0, the value is this. If the Hamming weight is 1, the value is this.
Yes,
it is an explicit function.
It will be a symmetric function.
Yeah, and it doesn't depend on the code.
It will be, instead of being, the indicator function of a ball of radius r, it will be some smoothing, but it will be still a symmetric thing. So the distances will all have the same weight. So it will not be 1 inside the ball, 0 outside. It will be sort of big inside the ball and small outside the ball.
Thank you very much.
And this will have this, you want from it this property that, AF times F is large. This you can get, this is clear how to search for such a function, because we know the eigenvalues of the Hamming cube. So we need to take it from, from the subspace where all the eigenvalues are this lambda. So then that's how we find it again. But still mysterious. I mean, it could be more.
I think everything about this problem is extremely mysterious.
I guess the point is that the function is helping you to prove that these balls actually almost cover the space. Because you could just take the balls, but the question is, why do they almost cover the space, right? And when you plug in this function in particular, you can manipulate algebraically and say, oh yes, indeed, because of this and this, these balls do cover 1/n of the whole space.
Thank you.
But they share somehow with Fourier that it would be nicer to understand it even better, right? To have even a stronger intuition about all those things, those bounds and techniques, to be very good. All right. So one remark, and let me put the bound there. So we have the two bounds, and we know that for distance half minus epsilon, they are quite off. They are quite separated, right? And one thing that Homogeneity observed, and Homogeneity has been a quite influential guy here with a lot of results, he observed that if you analyze, because Mac-Alice at all, they gave a feasible dual solution that established an upper bound. Potentially, it could be overshooting, right? It could not be capturing the maximum objective value perfectly. And what he said is that whatever you're going to derive using this LP, Delsarte LP, is not going to be too far off. So the rate is going to be at least the average of the GV bound and the MRRW analysis. So in a certain sense, the MRRW analysis is reasonably good. And in a certain sense, it's also telling us that the rate obtained that you can obtain from this method is very, at least for large distances, very close to epsilon square log 1 over epsilon, because you're just taking the average of the two. So in a certain sense, if you believe that the GV bound is the correct answer, which you have no idea, this method is definitely overshooting. The LP has a big integrality gap in a certain sense. Okay, Saramoginsky refined this result later, but I think this is a cleaner statement. So recall that for very large distance, the GV bound will be telling us that you can get something about epsilon squared, right? Rate epsilon squared, and this guy will be telling us epsilon squared log 1 over epsilon. But since you're taking just the average of the two, then this guy is going to dominate, right? For very large distance. So essentially, this approach is asymptotically is doomed to stay in the Michaelis at all. And but this was one way of coming up with a convex relaxation for this problem. That we have seen that it is equivalent to the lowest theta prime enhanced, right? And which is equivalent again to degree 2 sum of squares. But there is no reason to stop at level 2 of some hierarchy. You can come up with stronger and stronger SDPs to understand this problem somehow. And that's something that we are going to discuss now. Some way of trying to strengthen this. So it's as if the methods that we have seen, they are 2-point bound methods. They look at the difference of 2 code words and check their Hamming weight. But you could look at potentially larger collection of code words and check if they are if they violate minimum distance or not. Right? One such approach will be via sum of squares. Right, so let me.
Fernando, I'm just verifying that you're also speaking next week. So you have
yes.
Okay, good. So yes. Yeah, but maybe you planned more than.
Yes.
Okay, good.
So a lot of the things that I'm discussing here, if you want to see them in more detail, there is a short, crude course in my page that we explain the equivalence of Delsarte and the theta prime in more detail. We proved the first, the Michaelis et al. Result, the original proof, and so on. But it's a bit crude, so but it has we explain some of squares and a bunch of other stuff there. All right.
So Fernando, the SDP that you showed before, I guess like the exercises that you get from the actual equivalence that is rank 1. Are there any attempts to add some soft constraints?
How?
I don't know. I don't know how you actually establish an upper bound for this SDP, but
yeah, typically you need to go to the dual and try to cook a dual feasible solution.
That's how you establish it.
It
becomes an infeasible problem. I mean, SDPs you can solve if you put a run constraint that is.
No. So
soft one.
Some kind of soft rank. Like what's the rank of the upper bound that you get? I guess it's pretty big.
Yeah, in those SDP methods, I think we have no guarantee. It can be extremely large, right? That's true.
So,
but convex methods, you might be allowed to permute, right? If you have one and your problem has some sort of large symmetry, right? It might permute it all around, and you have no way of trying to enforce it's going to be very spiked. And this is a problem that has a lot of symmetries. So in some sense, it might be perhaps better to go to factor the symmetries before trying to attack this problem. I don't know, because otherwise you could take a feasible solution, permute it all over the place. That wouldn't be issue. But I think it's a good question. Anything that we have for understanding the independent set of a graph, you can bring here and then see what it gives. Right? It's a particular family of graphs that you want to understand the independence number. If there is, I haven't seen anything about soft rank in this case, but I don't know. Potentially you can use any convex programming technique that you want to attack this problem. But the very hard part is to analyze those programs theoretically, to somehow go to a dual or some equivalent form and give a bound. That's all right. Let me try to talk about generalization of those convex That's a different kind of generalization of complex programming techniques. So one thing that we did, we look at one code word for linear codes. Let's suppose that we are linear again. What we did, we consider a code word, and we looked at its Hamming weight, right? And we stored its Hamming weight somehow. That was the information that we're keeping track. But there is no reason to stop at one code word, right? We can take tuples of code words, x1, x2, x3, right? I can think that we're picking this in the code cube, right? And then you can store information about them. As before, you can store their Hamming weights, right? And then but that's not all that we can do, right? We can store the interaction of two code words. x1 plus x2, x2 plus x3, x1 plus x3. This is something that we allow to look at this kind of higher order information, right? x1 plus x2 plus x3. Let me just say that this part of the discussion is going to be based on joint work with Leonardo, that's there. So this is going to be based on joint work with Leonardo Corigliano. And Chris Jones. So what I'm going for is to come up with somehow a hierarchy on top of this. That somehow has a proven guarantee that to converge the optimal value. So here with Delsarte LP, we have no idea if it's converging to the optimal value. And if the G bound is tight, it's definitely not converging to the correct value. It has noticeable integrality gap. Okay, so we can store this information, the Hamming weight of all the interactions of code words, right? Here in this pane. Right? And more generally, we can look at what's called an L point bound. There is more work on this L point bound. So one very powerful hierarchy is the sum of squares hierarchy. That's you can use for the independent set. At a sufficiently high level, sum of squares guaranteed to converge to the correct value. But one difficulty of analyzing through SDP methods is that cooking dual solutions is extremely hard for them. We do not know in most cases how to cook dual feasible solutions for SDPs. Because on top of having linear constraints, you also have a PSD matrix that you need to make sure that's PSD. So you need to construct with your brain this family of dual solutions. So you do not know. And here you're going to try to shoot for an L point bound that happens to be an LP, a linear program. And that's going to be complete in the sense that's going to converge the true value of a code. We do not know this value of the code, but we know that in our hierarchy, if L is sufficiently large, it's going to get the correct value up to some very small error. And we can generalize this idea here, right? We can take larger and larger tuples of words, right? Belong to, I don't think that this belongs to Del, but let's be even more general. Belong to Del. And then one thing that we can define is the configuration of this guy. Bell configuration. Bell configuration is going to be config of x1, which the XL. This is going to be a function of the subsets of L to 0, 1. So it's going to measure. So let's say that this is a function phi. It's definitely a function that depends on the choice of x1, which for XL. And if you take a set S contained in L, what this function is supposed to tell us is the Hamming weight of their sum. So x phi of S is going to be the Hamming weight of the sum of the elements here. I belong to the set.
Simply the weight distribution of the code generated by this tuple.
Yes.
But order.
Sorry?
Order.
Yes, order.
Correct.
Yes.
which one is written as which linear combination?
As I said, right? You have this guy, and you're looking at the span of those words, right? And you are measuring the Hamming weight of the guys in the span of these words, and we are storing them. That's going to be our high order information, right? And out of this, we can define, since this is completely analogous to the weight distribution, we can define L configuration distribution, right? L configuration distribution. For this first, let's say if you're given some configuration, a valid configuration, let's say that here we have an H. Let me abuse annotation throughout. Let's say that this is a valid configuration, so some valid function of that form. Configuration, and we can count. We can look at this quantity here, AH, which is going to be the number of tuples x1, h2, xl belonging in situ the L, such that when you look at the configuration of this tuple, configuration of x1 all the way to xl, this is equal to h. Okay, so very analogous to what we did before, and then we can combine all of them. We can have a vector over all configurations, all valid configurations of our code. Over the configurations, and that's going to be the L configuration distribution. The distribution of the code. And as you might be suspecting now, we are going to have a notion of Williams identities here in this generalized setting. Right? So from an L configuration distribution of the primal code, we can generate the L configuration of the dual. So and for this we need to generalize the notion of Crotch of Polynomials. So, and that's not terribly surprising in the sense that all that we are doing here can be seen from the language, from a more general language of association schemes. And this is going to be one example of association schemes. And there is a general theory that tells us that the PSD-ness of these association schemes, they are equivalent to checking McWilliams-like inequalities. So in a certain sense, the equivalent follows from there, but you can prove the whole theory using basic reanalysis as we did. And you need to generalize higher order Crotches, right? Higher order Crotch of Polynomials. And it's going to be analogous as before, right? The original Crotches, they were of this form. Kij was the Fourier transform, right? So we have 2 to the n, the indicator of I, Fourier transform, evaluated at some S, and S had Hamming weight J. The high order version is completely analogous. You're going to have a configuration, let's say, G here, evaluated at H. What we're going to do, now that our space is much larger, is 2 to the L, and then we are going to look at the indicator of having configuration, of configuration, right potential. So the of configuration being equal to G. And then we look at the Fourier transform of this, and we evaluate this as an S1 all the way to some XL, where the configuration of those guys is precisely H. So the configuration is precisely H. Very good. So this is the high order notion of the Crotch. And then from this, you can also derive questions about the high order, completely analogous. So here we have the indicator of the sphere. now we have the indicator of this more complicated looking set. All the tuples that have a given configuration. So it's completely analogous, and we are going to have Williams identities. And with this, you can define a new linear program, a new family of linear programs, right? So here. New family. We call this Crotch of hierarchy. So we can define this Crotch LP hierarchy, and it's indexed by block length of the code, the distance, and the level. So this is, I think, at the level of the hierarchy. And it's going to be
just to get a sense of the number. Okay. So in n equals 1, we had n possible values. Plus 1 possible value for A. And we have something like n to the L. Right?
Yes. It's true to the L because of subsets.
All subsets. And
yes.
To the 2 to the L.
Yes.
Absolutely. Yeah, I guess for equals 1 is 2 to the L minus 1.
Yes.
Yeah. As n to the 2.
We have the Crotch hierarchy, and it's going to be completely analogous. We are trying to maximize the summation over all configurations here. So here you're summing G belonging to the set of valid configurations of AG. Now this is supposed to be the size of the code. This is supposed to encode C to the L instead of the size of the code. Right? C to the L is a feasible solution. And here you're going to have the similar constraints. So A of the zero configuration, the configuration that you get when you have the all zeros, the tuple, this needs to be 1, right? You have a linear code. We are counting, so we want all those coefficients to be greater or equal to 0 for all valid configurations. We have the Crotch transforms, right? Summation. Let's say G, K, H of G, AG. This we also have greater than 0 because we have high order.
AH of G.
Oh, sorry. All right, for every configuration we have G, this. And now it's the part that comes a distinction between linear and nonlinear codes. So everything that we said before generalizes for linear and nonlinear codes, but the constraints that we can impose in this hierarchy, they change drastically if you are working with linear codes and nonlinear codes. If you are working with linear code, because the configuration is in the entire span, right? And if it detects that there is a non-zero vector that has Hamming weight less than the minimum distance, it can set that configuration should be 0 because it's a violation. But for general codes, this may not be in the code. This may not be in the code. May not be in the code. So for general codes, the only thing that we can store is the single ones, right? Is the single Hamming weight of the tuples. But for linear codes, we can fully look at the span because they should all be code words, right? So that's going to change whether the hierarchy. So AG is going to be 0 for every configuration that's forbidden. And the forbidden configuration is something that sees a white non-zero Hamming weight vector. Forbidden configuration of a DL. So in the case of linear code, if your function, if the image of our function maps to something in this interval from 1 all the way to d-1, you need to zero out this configuration. And for general codes, you can only enforce this for singleton sets, right? All right. So and synthetically, this hierarchy is very it's moving here. Not giving a lot of details, but if you stare at this hierarchy and you stare at this hierarchy, the Delsarte LP, right? Structurally, it's very similar, right? And the nice thing about this hierarchy is that it's proven to converge, right? So let's two theorems here. So in this space, it has been hard even to come up with conjectures, even for linear codes, nonlinear codes, of what you should do in order to improve these bounds. So it's you're really as you have seen the state of the art. You have seen that the Gilbert version of bound is the best thing that you can do, and you have seen that the Mac-Ellis proof, right? That's also the best thing that you can do. So you have been really stuck in terms of parameters. So even coming up with bounds with approaches, right, that are proven to work might be useful. So one theorem that we have is that this hierarchy, the Crotch hierarchy, the beam as we go to larger and larger levels of the value of the Crotch hierarchy in BL. Here we need to take an LT fruit because we are supposed to get the size of the code ratio to L. This limit is the largest size. So here I'm going to work with the hierarchy for linear codes, and that index this with a lim here. So it's the hierarchy that has constraints for linear code constraints, and this gives us the largest size of a linear code in D. So that's
better than limit.
Well, yes, it's much better than the limit.
We're shooting our result. The result is much better than that.
Yeah, it's much better than this. But yeah, that's one first punchline of this is that it's extremely hard to analyze this guy. It might be much harder to analyze our hierarchy. But if you're here, we have no idea if it's giving the correct value. If the GV bound is tight, it's certainly not giving the correct value. You need better approaches. And if you are all powerful and can analyze this hierarchy, it will give you the correct value of a linear code, right? But again, analyzing those hierarchies is very hard. But at least the proven to be complete approach. And as Leo was saying, you can recover the correct value if L is about n squared in this hierarchy. So if L is about n squared, you recover. There are some.
There's the other thing, but okay.
You want to say the collapse of the hierarchy?
No,
no.
I want to say the level n thing, but
yes. It's still under verification that potentially, because what in this first proof that we had, what very crudely, what it did was like this. From Delsarte's LP or from this, is it easy to see that this hierarchy will get the correct value as you go larger and larger? It's highly, for me at least, it's highly non-trivial because you have this is going to be a multivariate polynomial, highly oscillatory polynomial. I have no idea what this program is doing. But somehow this program happens to coincide with a suitable theta prime formulation on a family of exclusion graphs. And from that alternative perspective, we could see some structure and see that this family indeed was getting to the correct value from that equivalent view. That's sort of why we quickly mentioned the theta prime formulation. But now supposedly we need to check that there could be a proof and our proof was only approximate in the sense that at level about this much, the value would be super close to this. It would be 1 plus epsilon. For I don't know, a very small epsilon you can deduce because the size of a linear code is 2 to some power. Right, and then you can recover the value. And now potentially we may have a proof that at level n, it converges exactly, which makes the hierarchy a little bit more natural. But yeah, it's still under verification, this one.
How to show a gap result like Samorodnitsky for the lower levels of your hierarchy?
Very good, very good. It works in the sense that if you try to do, you can.
What was the question?
If Samorodnitsky's method works for higher levels. In fact, it works for general association schemes.
Okay, but I don't know what association schemes are, so I'm just...
No. It works in general, but it might not give you good bounds a priori. That's the question.
It works, but now we're looking at something that's called the Hamming scheme, that you have the Boolean n cube, and then you have the adjacency matrix of when you differ by Hemingway 2, and when you differ by Hemingway 3, and so on. You have a family of graphs, and all that we discussed for Delsarte LP is intimately connected with that family of matrices. The family of matrices that are going to have now, they are indexed by configurations. So you're looking at pairs of tuples such that their difference lies in some configuration. And nicely, the homogeneity method is general enough that it applies, but you need to squeeze better bounds out of this homogeneity method. And for this, you need to make those choices, right? What is the function that you're going to look? What is the kind of, now you're in this product space. What is the kind of functions that you're going to consider in this product space and so on that would allow us to squeeze a better bound? And in this hierarchy, we don't know if, I don't know, it could be the case that the level 2 of this hierarchy gets very little improvement, asymptotic improvement. Could be we don't know, right? It could be the case that you need to go to level log L to see something happen. For all that we know, it could be the case that the LP bound that we have seen for MRW is the correct answer. So you might struggle analyzing this hierarchy and you're not going to see anything new because there is nothing, this will be the correct answer. So we are in this sort of stage that we don't know, but
it can only be correct asymptotic. Right.
You can,
we have numerical evidence that's not precisely correct. It can only be correct asymptotically. Right?
Yes, so potentially for it. Yeah.
Delsarte doesn't find the actual optimal code.
Yes. Even in a hierarchy, if you go to very large levels, it seems that this polytope that is defined is not an integral polytope when you're at the completeness level. It seems that you need to look at optimal solutions. So it's a weird polytope in some sense. All right. And the sad news is that if you try to do this hierarchy for general codes, since you can only impose very few constraints, it completely collapses. So if you can go as high as you want in this hierarchy, that it's equivalent to Delsarte LP. So you cannot use this method, unfortunately. And I think this shows some difference between for nonlinear, for general codes. Yes, for general codes, this hierarchy is the same as the Delsarte's.
It's possible. It's exactly because you just look at the Hamming,
yes.
So there's a proof that you should show that if you're not considering linear constraints,
things become a product in an easy way, and then you can sort of lift solutions.
The values are exactly the same. The optimum values are exactly
the same. And you guys were asking about difference between linear and general codes. This might be a place that the difference between linear and nonlinear codes might be manifested, right? This hierarchy works for linear codes, which might be a more structured setting, but it does not work for nonlinear codes. All right. Questions so far? No?
We'll first thank.
I should say that you are well equipped. So now you know what a binary code is. You know the state of the art. You are well equipped. You are as equipped as us to make progress on this problem.
So,
right,
questions? All questions to our audience, anybody?
So the analytic proof that you gave that relates the covering number of the lattice to the distance of the dual lattice, it resembles a lot things that like code and dual code, sorry. It resembles stuff done with lattices in our
yes.
Right? Where you look at the integral of a Gaussian, like the sum over a lattice, it's kind of like almost the same thing, only I'm wondering if there's also there is some LP or SDP business.
Yes. Very good. So my understanding is that for codes, we have had these McWilliams inequalities for a long time. And I think Henry Cohen, Noah, and Elkins, they generalized these McWilliams inequalities for the case of sphere packing. And it resembles, the theory resembles a lot. But I think there it's also known to have big gaps. If you want to pack asymptotically named, I think that they are exponentially far apart. Right. And they are, I think, I know very little about this, but I think lattices, there are many lattices that are very important. I think in dimension 8, dimension 24, and so on. And they really want to know the packing density exactly, right, for those small spaces. So And I would say that it's probably a hard setting potentially, because you're in Rn, right, and R3, you're in the continuous setting. Here you have more structure, right?
But SDP hierarchies give some real insights over there as well.
I know much less. I wouldn't be surprised if there is some SDP hierarchy there as well. I'll need to think how one could formulate some SDP hierarchy for packing. Because here everything that we did is very discrete, so it's easy somehow to come up with hierarchies, right? But there potentially need to be much more careful. But yeah, I don't know that. But what I know is that this theory of Williams inequalities influenced this approach, the LP approach there in sphere packing.
There's just the notion of this density that you had on the slices.
Some ratios.
No analog, right? I mean, it's.
You were saying the distance in the lattice.
The AIs.
I see.
It's just not clear if there is any analog to this business.
Yes, I understand little, but I think there is.
Sorry?
It can be a function, not a discrete. This is a function with n plus 1 value. This can be a function.
But in the discrete hypercube, there is a natural notion of the weight of a vector. And there it's just, I mean, there's just a Euclidean distance of the vector from the origin. That's the only parallel.
Yeah, I don't know much about the setting. I know that this setting influenced that setting, but potentially you can look at minimum distance of lattice and so on. One thing that I do not understand, now I have this hierarchy for linear codes. Is there potentially aligned with your question, an analog of a hierarchy that's much simpler for sphere packing, right, on lattices that somehow converge to the true value, right? It's not just some Delsarte LP. But I don't know much about that nature, so I'm not that nature.
Maybe I just remember the warning about lunch, so we can.
Yes.
Yeah. So thanks.
Thank you.